Aujourd'hui, on a le plaisir d'accueillir Denton Ebel. Donc, Denton Ebel est professeur au Muséum d'Histoire Naturelle de New York. Il est curateur de la collection de météorites. Il y est depuis 2001. Il a été undergraduate à Harvard. Ensuite, il a fait une thèse à Purdue. Et ensuite, il a fait des postdocs à Toronto. Et son premier postdoc était de la métallogénie. Et il s'est intéressé aux météorites que plus tardivement. Et il est très connu dans la communauté pour aussi le travail qu'il a fait quand il était à l'université de Chicago sur les calculs de condensation, donc de la thermodynamique pour prédire quels sont les minéraux qui se condensent à partir d'un gaz dans la nébuleuse. Alors il fait partie du science team de Messenger, et donc il va nous expliquer, faire un résumé, une vue générale de tous les derniers résultats et toutes les questions qu'on s'est posées et les questions qu'on se pose encore sur l'origine de Mercure et sa structure. Et ça fait partie d'un livre, c'est un chapitre d'un livre qui va être publié bientôt. Alors il est encore avec nous pendant 15 jours, puisqu'il est professeur invité à l'IPG. Alors vous êtes filmé, je vous rappelle. Voilà.
Bonjour. Merci. Merci. Nice introduction. I didn't understand all of it. Thank you all for coming on an odd day, a Wednesday, for the seminar. I will talk about the origin of Mercury from the point of view of the data we've obtained from Messenger, and then comparison with solar system phenomena that we already think we know about. And you all know, of course, that the Bepi-Colombo mission will launch very soon to go to the same planet, and they will find out everything that we couldn't find out, and they'll answer all the questions. So the origin will no longer be enigmatic, I hope, but that's a hopeful thing. The reason that I'm writing a chapter for a book about what we learned from the Messenger mission, and Sarah Stewart is an expert in impacts. And so you can't talk about Mercury without talking about impacts. I'll talk mostly about the chemistry aspects of what we found. So the first important thing to note is the anomalous nature of Mercury. Mercury is strange. It's not what you would predict from theory. It's not what we expected to see from Earth, and then now, of course, up close and personal. It has a very high density. It has a very low FeO content in the surface. In fact, in the world of spectroscopy of planets, we use the absorption of iron in olivine and pyroxene to tell how much olivine and pyroxene we have, but the absorption in the infrared. On Mercury, we can't do that. There's just not enough FeO in the magnesium silicates to even see the difference between pyroxene and olivine. We also have found out that there's a lot of volatiles, and what's interesting is the very high or very low albedo. Mercury is a very dark planet, and we don't understand why. So when we talk about the origin of a planet, we only have a few planets to talk about, terrestrial planets in particular. There's two kinds of process, and we keep these in mind all the time. One is sort of chaotic processes like Deus ex machina, right? It's just something hit Mercury and made it the way it is. That's sort of nice, but it's very stochastic, and it's not very amenable to science because it's sort of a random act of God, if you will, that makes this planet the way it is. The other kind of process is what I call a gradual process. And Clark Chapman came up with this dichotomy of two kinds of process back in the 80s to talk about Mercury. Gradual process would mean something that is normal on the innermost part of a disk around a sun, which might mean we'd expect Mercury's to be common around other stars as well. Very dense, iron-rich planets, small planets that are formed by a combination of chemical and dynamical processes. So I'll talk about too. So first of all, some of the data, the most important data for me as a geochemist, cosmochemist, is the composition data, the minerals, and most importantly, the elemental composition. So this is a schematic by Larry Nittler. This is so-called sunlight coming in, and this is the spacecraft. The spacecraft has an X-ray fluorescence spectrometer, so it can measure the spectrum of X-rays coming from the surface of the planet. And each atom emits X-rays slightly different energy. So, and the heavier the element, the higher energy of X-rays it needs to excite that fluorescence. So from the sun, as we approach solar maximum, we thought we'd have very high flux of X-rays to get lots of data. And we measure the sun's actual input energy through a little tiny hole in the sunshade. The first order of the mission, of course, is to use the sunshade always towards the sun and point these instruments, but always keep the sunshade near the sun. And the instruments are orbiting on a very large elliptical orbit, way out here, coming very fast. And we were in 8-hour orbits for a large part of the mission. And so all the commands had to be sent right away, days before, a day or two before, at least a couple of orbits before, when the spacecraft is out here doing the telemetry, because when it's going around the planet, we're not talking to it, really. So anyway, the X-rays come into the sun's energy comes in here, the energy hits the planet, emits X-rays. And this is an example of some of the footprints. This is during in 2011. This is footprints measuring. These are the measurements of magnesium over silicon, weight percent. Everything is in weight percent on these slides. This is the planet itself. I don't know if you know, the Messenger mission imaged 2/3 of the planet that had never even been imaged from space before. We'd seen about half the planet, a little less than half, from flybys back in the 1970s. So this was a huge amount of information came from this mission. But these are the kinds of footprints that the spectrometers could see as the spacecraft was orbiting the planet. And this is showing spectra. This is the unfiltered spectrograms. So this is M flare. This is a fairly low energy flare, solar flare here. Here's another flare here. And this is when we got great data. In September of 2011, we started getting really great data from, you can see this energy is going way up to higher energy channels up here to excite the higher Z elements. So just for comparison, these flares are measured in equivalent temperature. So this is an 18, blue is a large flare this was data published in a paper in Science, the original, the first orbital data paper, 18 million Kelvin. And then this is the M flare, this one here that we saw in July. But then in September, we start getting into really good stuff up here where we have very high energy and get out to where we can detect things like iron. And so this, just to get into the weeds a little bit, getting into the weeds means we're a little too much detail. But for example, sulfur is a very important element to measure. So this is sulfur is a very tiny little edge peak here. And we can really see it well in some of when we have 3 different filters, and we can see it very well in these 2 spectra here. So this is how the actual data is measured. I had a graduate student who worked on this. I had a postdoc with me for a couple of years. She's now back in Bern. She'll be working on Bepi Colombo using the same kind of data. So this is what results from this data. This is a MOWIDE projection, a map of the surface of Mercury, showing the heterogeneities in magnesium and aluminum. Ratio to silicon, there are certain assumptions. We need to assume a value for silicon in the surface that's sort of an average planetary value. And we see there's differences. This is Caloris Basin up here, the big impact crater. This is a region that's not associated with a known crater. Very high magnesium, HMR, high magnesium region, low aluminum here. And this, these are various, this is the northern hemisphere average plus the range, first 1 sigma range. This is the planetary average for these ratios. But what's interesting here is really how Mercury fits with the other planets that we think we know about. with the Earth, with rocks on Earth, periddotites, komatiites, and basalts down here, lunar and oceanic basalts. And this is sort of the northern smooth plains right here. This is this area on the top. It's an area about the size of the continental United States, and it's covered by what looks like a single flow. Very, very, very large, very low viscosity magmas on this planet. And we see drowned craters. There's a whole bunch of literature on that. This is this high magnesium ratio region right here. And this, EC partial melt, that is the composition of a partial melt of an enstatite chondrite in dark that was published on by Burbine in 2002 in Meteoritics and Planetary Science. This is the bullseye right here of the contours that describe what we see on the surface. Enstatite chondrites, they'll hear a lot about them in this talk. So one of the things we could also measure with the gamma ray, with the X-ray spectrometer, is sulfur and calcium. And I wanted to bring this up because, again, we have high sulfur associated with the high magnesium region, high calcium there as well. And iron. Iron, you see the coverage for magnesium, and aluminum is very large because we can use the quiet sun, the sun when it's not very energetic, to get footprints every orbit. When we start to get to sulfur and calcium, and particularly iron, which are heavier elements, you need much stronger solar radiation flux to excite the X-ray fluorescence. And that's why we have these gaps. We don't have footprints in these regions where there's gray here or gray here, which is unfortunate. The iron especially, we see this area is high in iron. What's very interesting is calcium to sulfur. Now, those of you who are igneous petrologists know that both calcium and sulfur are incompatible with mantle minerals, so they both erupt together. But this is an interesting suggestion that we may have calcium sulfides in the surface of Mercury. Calcium sulfide is oldemite. It's found in certain meteorites. So we do have meteorites that are as reduced chemically as the planet Mercury, that were formed by gradual processes, not by impacts. One of the other measurements that's exciting was done by the gamma ray spectrometer. So gamma rays are emitted by radioactive elements. We can also tell something about carbon and other elements from gamma ray spectroscopy. This is a classic plot of the terrestrial materials, potassium to thorium, roughly 55,000. Here, Venus, very spotty data. This is the Russian landers, the Venera landers. They lasted long enough to get gamma ray data, and that's great. This is where the Martian meteorites, the so-called SNCC meteorites, Shergottites, Knocklites, and Chessignites, fall. And this is Earth-ocean crust, and here's where Mercury falls, right here. So this is the moon. So we know the moon formed, well, we think the moon formed in a giant impact, and that the depletion in volatile elements, potassium, for example, is a signature of that event. So why do we plot potassium over thorium? Because thorium and potassium are both extremely lithophile. They go with the, well, on the Earth, they go with the granites. In all planetary systems, they rise to the surface with the least, the most polymerized melts. The residuals come out of mantles. And so, because thorium is very refractory, high temperature, sticks around, whereas potassium is very volatile, this is a measure of volatility effect, and we don't see any volatile effect at Mercury. So all of this information about the surface rocks has now, over time, the last couple of years, been turned into assessment of what is down below that we can't see, but we can see the expression of. And this relies on 100 years of experimental petrology done today, because, of course, nobody's been studying rocks at very, very low oxygen fugacity. They don't exist really on Earth much. But in the process of doing all of this, and I do not pretend to be an expert in this kind of geochemistry, but Stephen Houck in particular has worked on this using data from Olivier Nemours' work and other work to estimate from the planetary constants, the distribution of mass within the planet Mercury that we have from the spacecraft data, the surface data, what the parental liquids might be in the mantle of Mercury, have estimated the bulk planetary iron to silicon versus magnesium to silicon or sulfur to silicon ratios for certain assumptions. One of the most tantalizing ideas for the structure of Mercury internally is that there's a layer of FeS at the base of the mantle, top of the core, that acts to offset the very low density of the mantle, which has essentially no iron in it, with this lower mantle layer that's an iron sulfide layer, and that's represented here and here. And then what would be the possible silicon content of the core? And this relies on experiments. Luckily, Mercury is a low-density planet, or low-volume planet, so even though it's very dense, the pressures are accessible fairly simply in the laboratory. So we know that silicon and sulfur don't like to be with each other in an iron liquid. And we know that the core of Mercury is partially molten because it has a magnetic field, about 1/10 the strength of the Earth's field. So these are just estimates for different weight percent silicon in the core. And you can see that the enstatite chondrites, EH, EL, and these are another kind of chondrite called CB chondrites, and this is the sun here. And so we need a lot of silicon in the core to match the sun's iron to silicon ratio for the entire planet, and in which case we have extremely low magnesium. So Mercury is depleted in the element magnesium. Alternatively, we can look at this plot and say bulk Mercury, oh, well, we only need a smaller amount of iron in the core with an FeS layer, and we still have a depletion in magnesium to match the sulfur to silicon ratio. So these major elements just don't match up with things we know, like the composition of the sun, et cetera, et cetera. So just to summarize then, what have we learned from the Messenger mission? We've learned that the surface chemistry is extremely reduced. We already had evidence for that from Earth, but we now know it for sure. And I'm not talking, there's lots of other things about the planet that are fascinating, like polar ice in the permanently shadowed craters, like the existence of dike swarms found through paleomag from the actual spacecraft, all kinds of stuff like that. We know that it's got a terrestrial potassium to thorium ratio. It's got significant chlorine and sodium abundances in the surface rocks. It is not volatile depleted. It has a high sulfur to silicon ratio, perhaps much larger than the Earth's, but it has more or less chondritic major elements, lithophile elements here in the mantle and crust. We don't see huge. It's not missing the aluminum and calcium as maybe you might expect from a giant impact post-differentiation. And there also is a very high light element concentration in the core with the iron. And we're not sure whether it's mostly silicon, mostly sulfur, probably silicon. Also, very low albedo. These low albedo terrains are very cool because they're much darker than actually the Maria on the moon, which are very dark. But there's no iron, there's no titanium in the rocks on Mercury. So why are they so dark? Because on the moon we know that it's the ilmenite, the iron titanium oxides, and the iron in the silicates that darken the surface. We don't have those elements. Why is there such a dark surface? What we've discovered is that these low albedo terrains are associated with excavation by craters. And so the leading idea is that actually what would float in a Mercury mantle? What minerals? There's not enough iron in the melt of a Mercury mantle melt to float plagioclase, right, feldspar, as we see on the moon in the highlands. There's not enough of anything really except possibly graphite. Graphite would float in the Mercury mantle. And what we see is these excavated regions that may be the excavated early flotation crust that has since been overlaid by volcanics, but in fact is excavated in certain places, forming these very low reflectance materials. And so this could be a planet which had a graphite flotation crust when it started, which is very cool. Maybe involved with its origin, high carbon content, which is not inconsistent with the gamma ray spectroscopy. So speaking of reduction, this is a plot now showing comparing Mercury to other solar system materials. So this is the quartz phalite magnetite buffer. This is, well, it depends who you want to believe. If you want to believe Liz Cottrell, it is roughly the oxygen fugacity of the Earth's mantle. Maybe a little high, maybe QFM -1 or something like that. This is iron woodstite, FeFeO. So this is where iron and iron oxide can coexist along this curve as a function of temperature and the log of the oxygen partial pressure. These here are various types of meteorites. I won't go into the details. Diogenites are from Vesta. This is a palisite. Palisites are stony iron meteorites. They're olivine plus metal. These are various other meteorites, H chondrites here. These curves, this curve right here is if I take the sun and I cool it, the composition of the sun, very hydrogen rich, and I cool it and I condense minerals, this is something that I'll talk about in a moment again, I will be on this curve here. This is the iron woodstite, -6. This is extremely low oxygen fugacity, extremely reduced. That's this curve. And these curves are, if I enrich the solar system in dusts of carbonaceous chondrite composition, I increase the oxygen potential to these curves here. This is an intrinsic fugacity curve for ensitite chondrites of a certain kind, the low iron ones. And we know that these have a maybe 1 to 2 weight percent silicon in the metal in them. So the silicon content of metal is a measurement of how much oxygen was around, because silicon likes to make SiO2 and make minerals. The EH chondrites fall below this curve. So they begin to approach what we expect from Mercury's mantle in terms of the oxygen fugacity curve. And this is from 2016. Very, very reduced. Way more reduced than anything except possibly these ensitite chondrites. And I already brought those up in the context of partial melts that look like the Mercury surface rocks. I'm going to go through a couple of more comparisons with composition. Bear with me, I'm a meteoriticist, so I like meteorites and comparing things to meteorites. I'm going to compare two different models. So this is complicated. There's a lot of numbers here, but basically one model is has the iron sulfide shell underneath them at the base of the mantle. Various possibilities, but about a high percentage of silicon in the core. And the other has essentially no FES shell and has a lower silicon in the core and a higher sulfur content. There's a lot of uncertainties in these kinds of calculations. This is looking at a few of the properties of all these different kinds of rocks in the solar system. And this is an exercise. What looks like Mercury? What kinds of things that we know about can we compare Mercury to? And the answer is very little. The CB chondrites are the most iron-rich, carbonaceous-like chondrites. These are the chondrites here, the ordinary chondrites over here, and the more carbonaceous chondrites, the CI chondrites in particular over here, the solar photosphere matching the CI chondrites the most similarly. Sulfur to silicon mass ratio, well, these rocks, the ensitite chondrites can match pretty well what we see, what we model in Mercury, but the ensitite chondrites in terms of their bulk iron to silicon ratio, as we showed a moment ago, down here can nowhere near up here. In terms of bulk density, zero pressure density. So when we talk about planets like the Earth Mercury, Venus. One exercise is to take them apart, because the rocks that we're comparing them to in the case of chondrites are very low density rock, where pressure doesn't affect the density. Whereas something even as small as Mercury, a planet like Mercury, the uncompressed density is different from the actual observed density because the volume changed due to high pressure. So that's the only objects that match that are the CB chondrites, but again, they don't even have the right amount of iron to silicon as we see in Mercury. So nothing really matches in that context. This is looking at other kinds of data, more chemical data. There's a myriad of things here, but what I just want to focus on is the Institut chondrites, the EH chondrites, really come closer. If we take this model B, they match in terms of silicon to magnesium. If we look at the sulfur, they match also, but again, the iron just does not get there in the case of the Institut chondrites. One of the other things we can look at is generally what would match the volatile. So we saw that Mercury has a very high potassium, sulfur, and chlorine and sodium content, even compared to the Earth. So let's look at the Earth's volatility trend. This, the geochemists in the audience will know what this means. This is magnesium. We're normalizing to magnesium and to the carbonaceous chondrite standard. So things like calcium, zirconium, and hafnium, the rare earths, the refractory elements with a high 50% condensation temperature. That means if you take the sun and we cool it, these things will condense at very high temperatures into oxides, into silicates and oxides. Whereas these elements here condense at much lower temperatures. They're more volatile. And if we look at the composition of the Earth's mantle, we see that the silicate Earth has depletions in things like lithium, sodium, rubidium, zinc, etc., due to the fact that they weren't probably there to start with. The Earth was depleted in these elements when it was first formed. We see, of course, in the Earth's mantle that these elements went to the core, so they're very removed from the Earth's mantle. If we now look and add all of the, or at least a large fraction of the meteorite population to this plot, we have a mess, very busy mess. But let's look at it more closely. So the CR, CV, and CO chondrites roughly fall along this line. These are estimates by Ebel. The L chondrites, the ordinary chondrites, are close to the Earth, these triangles, very, very similar to Earth. The CM chondrites, which are very rich in matrix, the organics and fine-grained mineral dust between the chondrules and CIs and chondrites, are here. The Institut chondrites, lo and behold, are extremely volatile rich compared to all this other material. Once again, very much in agreement with what we see at Mercury. We don't have enough data to plot Mercury's abundance in its mantle of these elements, but it's probably higher than the bulk Earth in many elements such as sulfur, potassium, and sodium. So maybe Institut chondrites are a good analogy. So this is, now I'm going to run through some of the hypotheses for how we got this planet to start with. These ideas go back in time. Some of them are still being pursued, others are not. Aerodynamic sorting. So that's an idea that I'm not going to read the slide, but I will go through these in a moment. Evaporation of the mantle. So it's near the sun. Maybe the mantle just evaporated and was blown away by the solar wind. Early in the sun's history, it was very bright. It was brighter than it is today, perhaps very early, more active. Maybe the silicates didn't condense completely, and so Mercury formed from something that was poor in silicates but rich in metal. Maybe there was a different kind of dust and material in the inner solar system compared to where the Earth formed or where Venus formed that led to a different kind of chemistry in the condensates versus the gas that led to a different thing. And finally, the Deus Ex Machina, we had a giant impact. We know there were giant impacts in the early solar system. Maybe such a thing happened and caused the mantle to be stripped and lost. So let's look at this more closely. The first thing I'll talk about, aerodynamic sorting. So we have differentiated planetesimals. We see them in the asteroid belt. We see cores that are iron-rich asteroids, leftovers from planets being broken up. And perhaps as things drifted towards the midplane, the silicates broke into smaller and smaller pieces and were lost to gas drag into the sun, whereas the larger pieces, the core material of previous planetesimals, survived that process and then created to make planet Mercury. So this is an old idea, 1978, Weidenschilling. Stu Weidenschilling is a great modeler of this kind of process, but this is context. We see this far away. We try to determine what the heck happened in our solar system to make this what we see today, 4.5 billion years later. So it's a large detective story. I just recently, since I came to IPGP, was able to interact with Francesco and Sebastian and looked at some of their papers. This is a new take on an old idea where they're using condensation calculations in a nebula setting like this, where you use your temperatures, this is your pressures in the early disk out to 1 AU, and looking at how things would condense, and then if you strip them out of the environment where they were at T1, you would get an iron-rich residue, and then if you strip them out again at a lower temperature, the magnesium-rich solids out here. So this is a way to get at this same kind of settling into a midplane and radial drift of silicates versus iron-rich materials in a condensation kind of way, and they're finding that they're getting stuff. This is a lot like Mercury, this stuff up here. So that's a new idea. This is their paper in 2016. This is their newest paper, which is in press right now, and this is a different calculation, but the same kind of result obtains. But of course, you see this is 350 AU. That's about 10 times the orbit of Pluto right there. But qualitatively, we're seeing here the iron-rich material on the inside, and then silicates and ices and sulfides forming these different things. So there is active evidence in the context of models that this kind of process could have happened. So the next idea, evaporation of the mantle. So this goes back to Bruce Fegley, another person who's very active in the world of modeling planetary processes using thermodynamics. And this is an idea that the hot young sun would evaporate the mantle so that you'd get a very big core and very little mantle. And the key thing here is you would lose the volatile material much, much faster than you would lose the things like aluminum and calcium. Another idea is the condensation being incomplete. So this is my own work here at various total pressures and temperatures. As we cool something from a high temperature to a low temperature at a constant pressure, we can condense various things, calcium, aluminum rich material. These are refractory materials. And then we condense iron on the black curve and olivine on the red curve here. And we see that at high pressures, total pressures, we condense iron at about maybe 80 Kelvin higher temperature than olivine. This requires a very, very narrow window to separate one thing from another in terms of temperature space, this idea. Fourth, this is a work that I did with Colin Alexander before the Messenger mission, looking at the inflow and where you might have an ice line, and you might get carbon-rich dust actually passing through ice line where you would remove more of the water and possibly obtain carbon-rich material on the inside. Well, I'll go into that a little further in a moment. And then mantle stripping by a giant impact. So one of the objections to this model has been that, well, Mercury should show a very, very high depletion in volatiles, because the analogy is with the moon forming impact. So the moon is missing potassium, it's missing sulfur, it's missing a lot of chlorine and so forth. And the key thing here is that the Earth and the Mercury is not the moon. Mercury is the Earth. And the moon has been removed completely, not just put out there in orbit somewhere. So the analogy breaks down, because we don't expect Mercury to be so volatile depleted as we might have thought when the mission was sold to NASA. The Mercury, say, after a giant impact, would form a magma ocean. The ocean would basically would develop a crust very, very quickly. Volatiles associated with the atmosphere following an impact would reaccrete to Mercury. So volatile depletion is not a diagnostic of this model. It doesn't tell us that the volatile richness does not tell us that a giant impact didn't happen. What is the problem with this model is that it's very difficult to strip the mantle of a planet because it wants to reaccrete. Mercury goes around the sun every 88 days. If you made a cloud of debris and spread it around in that orbit, Mercury would reaccrete that debris very quickly. Well, maybe drag forces of solar wind and photons would cause that material to drift into the sun very quickly. Well, that cloud of material would be very optically thick. It would not see a lot of sunlight on the inside because of its optical thickness. It's not transparent. So problem here is that you really have a difficult time stripping a planet. And this is work that my colleague Sarah Stewart has informed me on in particular. So out of these hypotheses, what has been ruled out by the Messenger mission? 2 of the 5. Which is unfortunate, but that's the way it is. So Bepi Colombo is going to have to solve all these problems. We still have the possibility of sorting of material aerodynamically, Francesco's working on. We have the possibility of different kind of chemistry in the inner solar system. We know from the andesite chondrites that gradual processes in a disk can produce highly reduced material, very reduced material. And we also have evidence in meteorites that iron and silicates can separate from each other early in their history in the solar system. And we still have the possibility of some kind of impact, but it hasn't been properly modeled. So I'm going to go now into this particular story here very quickly and just run through that, some work that I've done that I think might be interesting from a point of view of condensation. What is condensation modeling? Condensation is what we think it is. It's going from vapor to solids or liquids. Modeling of condensation depends on 100 years of experimental petrology, spectroscopy, and quantum chemistry to understand the equations of state of gases, and then unifying this into models that describe large chemical systems by minimization of energy, and in this case it's the chemical potential energy as a function of temperature, pressure, and the bulk composition of the system. And if we condense the sun so we can hold it in our hands, well, maybe at 1,000 Kelvin, from high temperatures, we see it as temperature decreases at a fixed pressure, we see aluminum first, calcium next, titanium, and then the silicates coming out. And this is the fraction of total atoms, very small fraction actually, because the rest is hydrogen in a solar gas. And we get olivines and then pyroxenes, but as we continue to go further down in temperature, we'll start to get more pyroxene, olivine coming back in again at lower temperatures as we condense feldspars. This is the same data. Now the pressure is here. This is that single temp pressure. I've removed the vertical axis here. We don't have this information anymore of the amounts of stuff, but looking at the effect of pressure, 1 bar, 10 to the minus 8 bars. As we increase the total pressure in a system of solar composition, the partial pressures of all of the elements increase, so they condense at higher temperatures, eventually forming liquids at very high pressures over here. Now, one of the things that we've always been interested in is the stability of silicate liquids in a condensing solar gas. In these systems, we don't have any liquids whatsoever, but we see liquid droplets in chondrites as chondrules, silicate liquid droplets. So one of the things that I've worked on is how to solve this problem, and one way to do that is to enrich the system in a dust. So in a midplane of a disk, you might have concentration of dust that settles down from gravity into the disk midplane. Maybe we heat that again, and we form an enriched system, enriched in dust by factors of up to maybe 1,000, which is, astrophysicists say, maybe that's too high. But we can do the calculation, let's do it. If we go to those very high dust enrichments in a chondritic dust, we find that we get olivines with a very high iron content. This is the iron content of 30% at 1,000 times dust enrichment. But we also get large fields of silicate liquid, this brown field here. And that's consistent with the formation of the chondrules that we see in meteorites. So what Connell and I decided to do was to say, well, let's think about other kinds of dust in the solar system. Obviously, we could just say, let's add carbon, or let's add water, or let's add something else to this calculation. That's sort of ad hoc. What kinds of dust are there in the solar system that might represent a primordial material? Interplanetary dust particles are such a dust. So this is a chondrite, carbonaceous chondrite, about 5% carbon. There's a lot of organic molecules in them. This is the Murchison chondrite. There are a very low abundance of pre-solar materials, and there's water bound in them as well. The chondritic porous interplanetary dust that we collect in the stratosphere and measure in the lab is chondritic overall abundance, but anhydrous, very carbon rich, little tiny silicates that were definitively condensates from a gas that are sort of glued together with graphitic carbon, poorly graphitized carbon. And so we said, what about this dust? Let's use an analog to this particular kind of dust and enrich the system in that and see what happens. And so this is what we see. We see, first of all, in oxygen fugacity space versus temperature, as we cool the system, the chondritic dust gives us nice curves like this that are very similar to iron wustite buffer curve. Solar here. So remember, that was iron wustite -6. When we cool a dust-rich system, say 1,000 times in the IDP, interplanetary dust particle dust, we drop the oxygen fugacity like a stone. We get no iron in the silicates, and we stabilize other minerals because we're dropping the fugacity because the silicates are eating up the oxygen that's available. And what happens is we see, if we compare the two, now the dark curves here are the new IDP kind of dust, and the other is this is the curves for systems enriched in carbonaceous chondrite dust. And what we see is that the liquids, the solids, the olivine, the metal, very similar temperatures of condensation. So the pyroxene, metal, olivine, very similar. But what we get in addition is the stability of calcium sulfide and magnesium sulfide and iron sulfide at high dust enrichments. These are exactly the minerals we find in ensteig chondrites, and we may see calcium sulfide in the surface of Mercury. So that's an interesting exercise. What we also see is at high dust enrichment in this interplanetary dust material, we see that iron comes out at very high temperatures and silicon is kept in the gas phase for a longer time in terms of temperature cooling. So this is a solar composition. This is so we can reach higher iron to silicon ratios, but nowhere near what we need to get to something like Mercury up here. We can get a little bit above this line, but not much. So to summarize that line of research, we're trying to get funding to actually go into this more deeply because we've chosen a very conservative composition for the IDP dust. But basically, we see a lot of things that are very promising for explaining mercury, but we don't hit the holy grail of the very high iron content. So from that work, we have some assumptions, conclusions that there may be a gradual process that involves condensation that does predict something Mercury-like in the inner solar system, but we're not there yet. We don't have the high iron content, and unfortunately, we're not able with messenger data to truly resolve the pyroxene to olivine ratios in the surface of Mercury. The stability of minerals in very reduced systems may explain not only the enstatite chondrites, which are rich in potassium and chlorine and sodium and sulfur, but also something like the planet Mercury. So I'll leave you with that. We don't know the answer yet. Sorry, but Bepi Colombo is going to tell us everything we need to know, I hope, about Mercury, and I'm really excited to see what that mission brings. Thank you.
Y a-t-il des questions? Je commence alors. So
I've convinced everybody I'm right. Yes.
I start. So you showed that the map of the composition of Mercury, so you didn't comment at all on that, but they were extremely heterogeneous in composition, and so what's the story behind that? So
the heterogeneity of the composition is interesting. You're referring to things like this. There are a lot of debate about this heterogeneity, and in fact, in the models of the mantle and the possible starting compositions, what's down there, there's two parental magmas that might be responsible for the variation. And so in the messenger book, there will be a chapter about this, where there basically are two bulk compositions for the mantle that explain most of the variation in the two various terrains, particularly the high magnesium region and then those northern plains, which are the other extreme. So the people that do that kind of work have actually come up with that. When I then use that to calculate the bulk composition of the entire planet, the assumption is that there's roughly equal amounts of that primitive terrain, or primitive mantle material, but there definitely is heterogeneity in the mantle.
But this is heterogeneous matter which is exposed at different
which is expressing itself with very thin layers of volcanics. So we see pyroclastics on the surface. We see these flows that cover craters, that you can see the ghost craters poking through these flows, very, very low viscosity flows. And there's like a layer cake, it's like a phyllo dough of these kinds of materials going substantial thickness above what we think may be a primitive carbon-rich float.
Thank you. I was just wondering why you're favoring an institute chondrite composition, considering in the earlier slides the elemental ratios and especially the high iron content is a better match for the metal-rich chondrites?
Well, the metal-rich chondrites, like the CB chondrites, are not nearly as reduced as the enstatite chondrites, and they're also extremely depleted in volatiles as well. So but the enstatite chondrites are not so metal-rich either. They're the most metal-rich of all most of the carbonaceous chondrites, but the CB chondrites are more metal-rich. But then again, and the other reason I would disfavor that is that there's in some people's minds there's very strong evidence that the CB chondrites were formed in impacts, that they don't reflect a gradual dust accumulation and melting process that is most reasonable to explain the most of the chondrites that we have in the record. So the other thing is the N-site chondrites fall bang on right there, whereas the partial melts of them do, whereas that's not going to be the case for the CBs.
Sorry. I was just going to shout. I asked you this in the pub, but I didn't get the answer to it today. So why do you think Mercury is so reduced?
Is so reduced.
Yeah, why?
Well, I would suggest that it's formed from a very carbon-rich inner solar system.
What's the evidence for it?
Oh, it's the lack of FeO in the silicates on the surface is the most first-order reason. There's not only is there extremely low iron content, less than 2 weight percent iron, not FeO, iron itself, in the surface rocks. And that's an upper limit because of the detection limits of the X-ray fluorescence spectrometer. The other thing is we knew that they had very low FeO in the silicates. If you compare, for example, to the lunar Maria, they have like 15 weight percent FeO in the olivines and pyroxenes. We just don't have that here at all. We can't even see in the infrared spectra. We can't see the absorption features of the iron in those silicates. And laboratory spectra say that means that they have less than 1 weight percent FeO in the silicates. We thought maybe that this was due to space weathering. What space weathering does on the moon is the volatilization and recondensation forms nanophase iron particles, which are pure metal. But we don't see that either. The absolute composition in iron is so low.
Is it really the case that low FeO has to be low?
Well, it could mean that there's just no oxygen there to begin with.
And also in the Earth, it's a slightly more familiar, right?
Well, either we have a overabundance of.
I mean, it's clear that there's no FeO. I'm not arguing.
Right.
So
is low FeO is zero FeO?
I mean, does that really mean you've got a low activity of oxygen in the system?
Yeah, I think it does. If the planet formed with a very, very low abundance of oxygen totally, I mean, FO2 is a partial pressure measurement, right? So it means that there's no oxygen there. If there were oxygen, it would form FeO in silicates. It would oxidize the iron that's present in the planet itself, and that iron would come out of the mantle out of the core into the silicates. So if the oxygen had been there, it would have made FeO in the silicates. The FO2 is a measurement of the lack of oxygen in the entire system. If you vaporized mercury and filled this room with the vapor of mercury, including the core, you would have the fugacity of oxygen, the negative log partial pressure of O2 as a gas would be very low, like iron wustite -6 low. That's what that says.
I mean, basically, you've got a pocket of oxygen.
You have to not have had oxygen there to begin with. Right. So if you have a high carbon, so what fixes the FO2 of the solar system? Is the CO molecule eats up the oxygen and the carbon. Once you've eaten up the carbon by adding oxygen to it to make CO, then you can start to make oxides. If I have a solar system which is depleted in oxygen so much that I use up all the oxygen to make the CO, then I start making carbides instead. So I make iron carbides, I'll make silicon carbide, I'll make titanium carbide instead of oxides. So the CO ratio of things is fundamental to the chemistry that we get from those things. This planet has an extremely high C to O ratio in its formation. Maybe. That may be the reason why it's so reduced, is that the oxygen got eaten up by C. That makes a gas that dissipates in the early solar system by a mysterious process we don't really understand. Do we, Sebastian?
So I have a sort of follow-up question, naive question from a seismologist, is about carbon. How do you know there's a lot of carbon? It seems that you infer it indirectly.
We infer it indirectly. There's the low albedo, the low reflectance regions are so dark that it's hard to imagine what, there must be something that makes them dark. Sulfides can be dark, that's true. And we have a significant fraction of sulfur in the surface. The gamma ray spectrometer is best for measuring radioactive elements, but it can also measure abundances with very large error bars of some other elements, better than others, and because they absorb cosmic rays and then they give off gamma rays of various wavelengths. And what the gamma ray spectroscopists have shown is that there could be up to 4% carbon in these materials that are the low reflectance materials on Mercury. There could be zero, but it could be up to 4% would be consistent with the gamma rays spectroscopy. That's really the best evidence that we have. It's unfortunately not good enough, but it's there. And what would float in a magma ocean on Mercury? Graphite is about the only mineral that is made of abundant elements that would float in that magma.
I can ask you maybe a last question. When you presented the model of the giant impact, and you were saying one of the consequences will be depletion in incompatible elements, right?
Potentially. If the Mercury differentiated and you had a crust which was rich in aluminum, calcium, potassium, then a giant impact would
Yeah, but you would blow all the metal, no? I mean, all together, so it will remelt everything. So you think it
would deplete a lot of things.
Yes, not just
and the models that and what Sarah is, what we conclude in our chapter is that in fact mixing in a large impact is so pervasive that no part of the mantle would be preferentially stripped. The core would be less stripped than the mantle, but even that would be severely disrupted. What Willie Benz has done is we wouldn't expect the incompatibles to be preferentially stripped because the entire mantle would mix completely with everything, with the impactor. Willie Benz's calculations of these kinds of impacts being catastrophic, you really need to nearly destroy the entire planet to get the kind of stripping that you need to get that much enrichment in core. And the problem is that the reaccretion is very efficient to that core. There's other models that are say, well, if you had a giant impact and then you had another body that was nearby that could, so the Russians have in some years ago now had ideas that Mercury was closer to Venus early. Therefore, series of small impacts could send material that would then reaccrete to Venus, not to Mercury. Okay, that's sort of ad hoc. There's another idea, the hit and run Eric Ashfog model, which is that Mercury is hit by a very, very large object, but a glancing blow, so it's like a hit and run, and that large object then accretes the mantle material, but Mercury is dragged away, the core mostly, to in some other direction by another body. Strange things happen in solar systems, you know. I mean, Uranus is orbiting on its side, right? It's a giant impact, must be. Deus ex machina.
Yeah. So perhaps the last one. So from what you know on Mercury now and what you know on meteorites, you are sure that we have no piece of Mercury in our meteorite collection?
There's one so-called Mercurian meteorite, but the FeO content of the silicates would be measurable by a spectrometer, infrared spectrometer, so it's not from Mercury. There are meteorite dealers who will tell you that they have a piece of Mercury. So you better buy that piece from them and then do some spectrometry and isotope chemistry. But I know, so far, no. But there are calculations, reputable calculations, showing that you could indeed launch something from Mercury in a giant impact, big impact, and have it reach the Earth. So there might be pieces of Mercury in our collections. There's no way we'd know. We need sample return from Mercury. I think the young people here, that's a good mission to propose. Yeah, John's going to do that, or Rick. Yeah, sample return from Mercury. Be nice, be great.
Okay, thanks. On peut continuer la discussion autour du buffet si vous voulez. Thanks again.